flipbook. We have 3 sections in chapter 5. We're going to talk about 3 sections. So, first things first, flip the paper over onto the back and write your name. Flip it back over to the front. 5.1, we talk about mid-segments. 5.2, which we'll get to today, is perpendicular bisectors. Perpendicular bisectors. If you want to make it all pretty, you can draw your lines in there, doodle a little bit. And 5.3. 5.3 is angle bisectors. 5.1, mid-segments. We talked about mid-segments. Draw yourself a triangle. To find your mid-segments, what do we say we do? We find the middle of one side so that those parts are now equal. We find the middle of our second side so that those parts are equal. We found our 2 midpoints, as Mason was asking. You just guessing, or what are you doing? Right now I am. If I was actually looking for the mid-segment, I would do this. I would get out my ruler, and I would measure that, and I say, hey, if that's like 4 centimeters, what I would do is I'd say, well, what's 4 divided by 2? 2, so that that's 2 centimeters, and that's 2 centimeters, and that's exactly the middle of my line segment. So we could measure it with a ruler. If it was on a piece of graph paper, we could graph it. We could use the midpoint formula to find the midpoint between those 2 points, right? So 2 different ways to do that. Right now, just for the sake of time, yeah, I am just eyeballing it. So same here. Where's the middle of this side? Approximately in here. And if that's the middle, that makes those equal parts. Or congruent. Yes. Drawing your mid-segments. Take 2 midpoints, we connect them. That's your mid-segment. Here's 2 midpoints. We connect them, there's a mid-segment. 2 other midpoints, connect them, there's your mid-segment. Every triangle has 3. So what 2 things did we say we know about this? We know mid-segments are parallel, and also we know one of them, we say one is half as big, one of them is half as big, or the other is twice as big. One is half as big, or the other is twice as big. So here's an example. You have a triangle. We sketch in our mid-segment. What do we know about these 2? The mid-segment is parallel to the third side. Those are parallel. And let's say this is 5 centimeters. Your mid-segment is 5 centimeters, so this side would be 10 centimeters. Very good. We've got a triangle. You've got the mid-segment, which is 4x minus 1. This other side is 5x plus 4. And the instructions say, find the length of the mid-segment. Two of these make up that one, right? It's always 2 of the smaller one. The smaller one is always going to be the mid-segment. So, first of all, find the length of the mid-segment. What we need to do is take the mid-segment, and multiply by 2. Take the mid-segment and multiply it by 2. Alright, so you guys are already setting it up. You're going to it. The smaller one, we have 4x minus 1, and set it equal to The other one, if we have parentheses we need to distribute through. 2 times 4x gives us 8x. 2 times a negative 1 is a negative 2. And bring down the right-hand side. Subtract your 5x over. 3x minus 2 equals 4. Add your 2. 3x equals 6. We divide by 3. And my x value is 2. Aha. Aha. Good, Justin. So Justin's like, hey, Mr. We're not done, though. You got to take that x equals 2. The question said find the length of the midsegment. So plug it back in up here. We have 4 times 2 minus 1. 8 minus 1, as Justin said, gives us 7 for the length of our midsegment. How do we check and how do we know that we did it right? What if I plug 2 in here? What's 5 times 2? 10 plus 4 gives us 14. If this is 7 and that's 14, does that make sense? Is one twice as big as the other? Yeah. That is midsegments. 5.2, we are using perpendicular bisectors. The first objective, I can identify and use perpendicular bisectors, and secondly, I can identify and use properties of equidistant from the endpoint. Let's stop. Let's see what we know already. What does perpendicular mean? It means they intersect at a 90-degree angle. What's bisector mean? It's like you have a line segment here. A perpendicular bisector, it's perpendicular to it and it bisects it. So it's like bisecting another segment or another line or another ray. And if I say equidistant, what do you think equidistant would mean? Equal distance, right? The same length, equal distance. Let's jump in here. Perpendicular bisector, a segment, ray, a line, or plane that's perpendicular to a segment at its midpoint. A segment, ray, line, or plane that is perpendicular to a segment at its midpoint. Perpendicular to a segment at its midpoint. And equidistant means the same distance or equal distance, same length, same distance. Equidistant. So, you ever been driving down the road and have you seen a bridge like this that has like those support beams coming down? Maybe not this specific one. I know that when I drive to Detroit to see a friend, there's a bridge that looks very similar to this. So here's what this is. This right here, like in real life, that's where you might see a perpendicular bisector. This comes down, and then what I have is this distance is the same as that distance, and this one is the same as the one next to it. That means that if those are the same distance apart, these are going to be equal distance apart in here too. So it's perpendicular, and it bisects it because those two parts are equal. Okay? That's just a real-life example to show you. The perpendicular bisector theorem says this, though. So watch and pay attention to make sure you catch this. In a plane, if a point is on the perpendicular bisector of a segment, if a point is on that bisector, I got this point out here, then it is equidistant from each of the endpoints. Then those two distances are equal to each other. We also have the converse of this. The converse of the perpendicular bisector theorem says this. If a point is equidistant from the endpoints of the segment, so if this distance and this distance are the same, this point is going to lie on that line if I were to continue it. And some of you are thinking, Mr. Oak, you've told us you can't just assume anything. If we continue that line, some of you are like, Mr. Oak, that line's not going to go through there. If this is true, if this length and this length are equal to each other, though, that point will lie on that line. That's what the theorem says. So what's this mean? Line BD is a perpendicular bisector of AC, and we want to find AD. Label your picture. Line BD is the perpendicular bisector. If it's perpendicular, you've got a right angle in there. And if it's bisected, those two parts are equal to each other. And if I have this point out here, that tells me these segments are also equal to each other. So the perpendicular bisector, they intersect at a right angle, those two parts are equal, and if those segments are equal, those segments are also equal. So set them equal and solve for x. They're equal, so we set them equal, and then we can solve it. Work it out on your paper, see if we get the same thing. So we get 7 equals x, or x equals 7. What property is this when I take and I flip it? Symmetric. We take and we flip it, that's your symmetric property. Good, going back to first trimester, see what you remember. Am I done? Did I solve the question? Did I solve the problem? Plug it in. It says find AD. Well, here's AD. I got to figure out how big that is. Use my x. 5 times 7 gives us 35. How do I know I did it right, though? Plug it in the other side, right? So 3 times 7 plus 14. 21 and 14 gives us 35. Did we do it right? Yeah. Pretty it up. Clean it up. What did we say? We're finding AD, so tell me AD equals 35. How about here? In the diagram, line WX is the perpendicular bisector of YZ. I'm like, hold on. Let me look at my picture and figure out what's going on. WX is my perpendicular bisector of this line. So if it's bisecting, that tells me those two parts are equal, right? Mark your picture, draw on it so you see what you're talking about. What segment lengths are equal? Raise your hand and tell me what segment lengths are equal. Yeah, 25 and 25, those are equal. They're both labeled the same. So how do we name it? How do we name this segment right here? YV is equal to ZV. And I like the order you guys put that in because my Z's are last. They have to correspond. They have to match up. YX is equal to what? ZX. And again, I am going to be picky on you. Your X's must go last. We've been working with this a long time. Your X's have to match up. YX matches up to ZX. If I were to fold this in half on top of each other, they'd match up. ZW and YW would also match up. Yeah. And again, those W's are last. They have to match up because they're in the same corresponding location. Is V on line WX? Well, how do we know? How do we know V will be on that line? It might not always be true. How do we know it is this time? Because what? It has arrows. It's going to extend, but what if it's off by just a millimeter? What properties, what theorems prove to me that must lie on that line? This point will lie on this line if this is true. If this segment, oops, let me just do 2 in here. If this segment is equal to that segment, we say yes, that point will lie on the perpendicular bisector. So, is V on line WX? We say yes. V is on line WX because, we're not writing cause, C-U-Z, like you're texting your BFF, right? Because, yes, V is on the line WX because what? This segment is equal to that segment because YV equals ZV. I can guarantee you will see questions like this come up again and again and again. Make sure you get it so you can kind of do fill in the blank. Supposing it's a different example, bless you, you can fill in the blank here. Why is that on the line? Because those two parts are equal to each other. That's the lesson in a nutshell. Let's practice a little bit more, though, till I let you go on your own. In the diagram, JK is the perpendicular bisector of NL. So I come to my picture, I'm like, all right, what does this mean? JK is perpendicular bisector. Don't forget that word bisector means that those two parts are equal. If it's a perpendicular bisector, splits it into two equal parts, they intersect at 90 degrees. What segment lengths are equal? And explain your reasoning. Raise your hand and tell me what segment lengths are equal. NM equals LM. Good, because those are both marked with 8. What's the second one? Somebody I haven't heard from. So LJ and NJ. And again, those J's match up because we're being picky on you. And then, good, KL and KN. KL equals KN. Who finds NK? How are we going to find NK? Here's NK. Set them equal. This is equal to that one. You can tell by the marks in the picture. They're the same, they're marked the same, so we set them equal. So you have 6x minus 5 equals 4x plus 1. You solve it, and when you're done, look up here and see. How we do? Did you plug it back in? X is equal to 3. If I plug that 3 in, we get 13 for both sides. They match up. They're equal. And again, you can kind of think of this. If you take it and fold it in half on itself, you've got your like parts are going to match up and they're going to be equal to each other. And lastly, number 3, explain why M is on JK. Why will M lie on that line? How do we know? Watch this. Why does M lie on this line? Plain and simple, because this part is equal to that part. So we say M is on JK because, that doesn't need a comma. M is on JK because MN equals ML. Or if you said NM equals LM, that'd be fine too, as long as your M's match up. We're getting there. Let's fill in those last definitions. Concurrent means 3 or more lines, rays, or segments that intersect in the same point. 3 or more lines, rays, segments that intersect in the same point. Concurrent basically means they intersect. If I say point of concurrency, I'm just talking about the point where they intersect. So it's the point of intersection of lines, rays, or segments. Concurrent means they intersect. Concurrent means they intersect. Point of concurrency is where that occurs. A circumcenter is the point of concurrency of 3 perpendicular bisectors. Circumcenter is the point of concurrency of 3 perpendicular bisectors. So check out this theorem. Concurrency of perpendicular bisectors of a triangle. The perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices. Underline that. Equidistant from the vertices. Or on the back side of your note sheet. Equidistant from the vertices. What are the perpendicular bisectors in that picture? The red or the blue? The perpendicular bisectors are the blue. Good, Kaylee. This is a perpendicular bisector. This is a perpendicular bisector, and this is a perpendicular bisector. This place where they all three intersect, that is called the circumcenter. It is the point of intersection, but it's got a fancy name. The point of intersection is called the circumcenter with perpendicular bisectors. Nope, not three-dimensional. I'm just drawing in the perpendicular bisectors where they intersect is called the circumcenter. And my theorem says the circumcenter is equidistant from the vertices. What's a vertice? What's a vertex? The circumcenter is equidistant to the vertices. What are my vertices? It's like your angles or your points, yeah. The circumcenter is equidistant to the vertices, to each of those points, A, B, and C. Check this out real quick. You have these on your paper. If I give you an acute triangle and I say, hey, here are the perpendicular bisectors, the place they intersect with an acute triangle is inside the triangle. If I draw in the perpendicular bisectors on this one, if it's a right triangle, the place they intersect is actually on the triangle. And if I draw in my perpendicular bisectors here, the place those intersect, if it's obtuse, is outside of the triangle. Okay? Just so that you're familiar with those. Here's what we're doing for tomorrow. Some of you need to finish your homework from last night and bring it tomorrow. On the A side of your worksheet, you do questions 1 through 4. On the B side of the worksheet, you do 1 through 3. The top section on both sides.